Is Agnes Lamacz, talk about refractive Maxwell equation and the flat things and files.
Yeah, so thank you very much. Okay, so in the following, I will present a joint work with Ben Schweitzer from TU Dortmund and explain how a particular microstructure can affect the phenomenon of negative refraction. The talk is organized as follows. So in a short introduction, I will first motivate and explain the concept of so-called negative index materials and illustrate the connection to Maxwell's equations. Afterwards, we'll continue with a mathematical description of the problem, a homogenization, multi-scale problem, in fact, and a statement of the main result. And finally, I will also provide insight to the main ideas of the proof. Okay, so refraction of light, as you can see here, is of course a well-known phenomenon. What happens is that at the interface between two media, the wave's phase velocity is changed, resulting also in a change in the direction of the light ray. Actually, this happens according to this famous Snell's law of refraction, and thereby the crucial quantity is this n here, the frequency-dependent so-called index of refraction of a medium, which is a material parameter, basically defined as 1 over the relative speed of light in that medium. Okay, now of course, refraction takes place not only for light, but for any electromagnetic radiation, whose dynamics is described by a system of PDEs, namely the Maxwell's equations. So in the Maxwell's equations, one has two vector-valued variables, E and H, in 3D, where E is the electric and H the magnetic field. Now our aim here is to study the time harmonic system. That is, for a fixed prescribed frequency omega, we assume that the time dependence of our fields is of the form exponential to the minus I omega t, where this omega appears also on the right-hand side of the equations, basically in place of time derivatives. Now, particular attention has to be paid to these two complex-valued material parameters, mu and epsilon, the so-called relative permeability, the mu, and the relative permittivity, epsilon, whereby the imaginary part of epsilon is strongly related to the conductivity of a medium. So high imaginary part means high conductivity. And actually what is the main point for us is that these two material parameters already determine the index of refraction. So there's a very simple relation between them. Now, remembering the previous slide where we introduced this refractive index as simply 1 over the relative speed, it is of course very natural to think of this n as a positive value, which in fact, in practice, is the case. However, in 1968, the physicist Victor Veselago theoretically investigated the question of what would happen if the refractive index of a medium was a negative number. Just a theoretical question. And he, for instance, found out that, among other things, Snell's law still would make sense, and that in the case of one medium with a positive index and another medium with a negative index, light should be refracted somehow backwards, causing this very impressive effects. Now, while there actually exist materials with a negative permittivity, more precisely the real part is negative, which is the case for many metals, all natural materials have a positive permeability mu. The real part is positive, which is usually very close to 1. So in particular, there exists no material in nature for which both the real parts of the permittivity and of the permeability are both negative at the same time. But this is exactly the configuration which is needed to generate a negative index in the sense of Veselago's study. So since such materials simply do not exist in nature, the ideas of Veselago remained purely theoretical for a very long time. And it took something over 30 years until the first actual negative index material was constructed, namely by Pendry and his group. Okay, so this artificial material, I mean, of course, it has to be artificial because materials in nature don't have this property. It has a fine microstructure consisting of many small, flat, periodically distributed rings or double rings in this case, with a very thin slit, so-called split rings. And the split rings are made of a very highly conductive material. Moreover, very thin, metallic, highly conductive metallic wires are running through the rings, as indicated here also in the sketch. Now it is this microstructure which makes the material, at least effectively, behave like a material with a negative index. So it's a homogenization effect. Electromagnetic waves with a large wavelength, it's large compared to the size of those rings, they simply do not experience the small internal structure. Instead, the material behaves like a homogeneous one with an effective index of refraction, which indeed turns out to be negative. And this has already been confirmed experimentally, while the mathematically rigorous derivation of this effective index, this is the main result I will show you today. Okay, so before proceeding, let me say a few words on the different roles of the rings and of the wires, because it will be really the main principle that the effects of the rings and the wires are somehow decoupled. And it will turn out that the rings alone, so without the wires, are responsible for a negative permeability, mu, which is of course a much more sophisticated effect because, as I said, all natural materials have a positive mu, so something very non-trivial has to happen in order to obtain a negative one as an effective behavior. And then the wires create independently of the rings a negative epsilon, and then both effects together lead to a negative index at the end. Okay, so let's formulate this in mathematical terms. And so in the following, we will be considering a scattering problem, where we assume that we have a scatterer, this object here, which is made of the small split ring wire structure and which is illuminated from outside by some incident wave. Now, for the microstructure, assume, and I will make this more precise in a moment, that it consists of a periodic repetition of small split rings and wires with some periodicity length, which we call eta. So eta for us will be a small number representing the typical size of the rings. And let me just emphasize that usually in homogenization, of course, the small parameter is called epsilon, but here it's the permittivity, so we call it eta. This is the small parameter in the system. Okay. And actually the main result that I will show you will be basically of the form, not exactly, but basically in the form that in the limit as eta goes to 0, so as the microstructure becomes smaller and smaller, the effective equations are again Maxwell's equations with effective parameters mu and epsilon. And indeed, it will turn out that with the right choice of the microstructure and for a certain range of frequencies, both the real parts of the permeability and the permittivity can both be negative at the same time. So this is, of course, the situation in the scatterer. Outside the scatterer, where no microstructure was present, we just get some constant values. We choose mu and epsilon just equal to the identity matrix, so just equal to 1. So outside nothing happens. This is the situation in the scatterer. Okay, now let's go one step further and zoom a little bit more into the microstructure. So in the following, we will assume that a single periodicity cell contains one split ring and 3 wires connecting opposite faces of the cell. So let me maybe comment on this. So actually, the usage of 3 wires here instead of only 1, as you have seen on the picture before, this is just for convenience. Because with 3 wires we get isotropic effects, and this is not the case with only 1 wire. So this is just for computational convenience. The other point is that here the wires are not running through the rings. Yes, they stay away from the ring. And this is also just for convenience. So we could obtain the same results with wires running through the rings, but the computation, the results would be much less transparent, and so we decided to keep them away from the rings to really see the effects more clearly. Okay. Now, as already mentioned, the main principle here is that the effects of the rings and of the wires are decoupled. And so for this reason, the talk is also split into 2 parts. In the first part, I will explain the effect of the rings alone, without the wires. So we'll completely forget about the wires in the first part of the talk. And then in the second part of the talk, we will add the wire structure and see how the wires act and why, and in particular in which sense the effect is decoupled from the rings. Okay, so let's start with the modeling of the split ring array. And yeah, as already mentioned, we assume that we have a periodic repetition of small split rings of typical size eta. And before discussing the scaling, let me comment on one important thing, namely the shape of those rings. So as you can see here, when talking about rings, I don't mean perfectly circular rings. So this is not just an accident, it's not really circular. And in fact, this is important. So the shape of the rings is arbitrary in our approach. This is important as in practice, as you have seen, the ring shape is not necessarily circular, so many different ring shapes are used. So the picture before, we had square rings. And in this context, I would like to mention also an important paper in this context by Duisburg-Essen and Ben Schweitzer from 2010. I will give you a reference to this a little bit later on, which was the first one which analyzed such a split ring structure. However, in that paper, the shape of those rings had to be circular, so the proofs were relying on the specific shape. Here, we get rid of this, so our approach is valid for general ring shapes. They do enter the effective system, of course, but this is arbitrary. And I mean, of course, this is important also because this paves the way to more complex questions like, for instance, shape optimization in the context of such negative index materials. But we didn't do this so far, so, but it's possible. Okay. Now back to the modeling. So since in practice the rings are very thin, as you have seen, and the slits are very thin too, we impose that a single split ring has thickness of order eta squared, meaning relative thickness, so relative to its size of order eta, very flat, and that the slits are even thinner, namely of order eta to the 4. Now, in order to model the high conductivity in the rings, we set epsilon eta to 1 plus I times kappa, some material parameter, over eta to the 3 in the rings. So very, very high conductivity in the rings. And we set it simply equal to 1 outside. Now, note that all the complex behavior of our microstructure is encoded in the single parameter epsilon eta, which depends on eta in a very complicated way. Because we have a high contrast, we have rings which are flat with very thin slits, many of them, but everything is encoded there, in fact. And by the way, the permeability, so the important point in this first part of the talk, this is set equal to 1 everywhere. So in the rings and also outside, it's constantly equal to 1. And actually the question I would like to answer now is what happens in the limit as eta goes to 0? And the answer is the following. So assume that H eta and E eta is a solution to our Maxwell system with this high contrast permittivity epsilon eta, permeability equal to 1, and a radiation condition at infinity, so scattering problem. Assume further that H eta and E eta have weak L2 log limits. So in fact, this can be shown. You don't have to assume it, but let's assume it here. Then, this is our main result. There exist constant matrices, hat M and hat N, which we can calculate, so really formulas for them, such that the limit functions H and E solve the following effective system. And for the moment, forget about these 2 lines here, just have a look on this effective system. And to be more precise, this is again the situation in the scatterer. Outside the scatterer, hat M and hat N are just equal to identity. Yeah? Okay, so let's have a look on this effective system. And actually, there are 2 things you should note. The first thing is that the first Maxwell's equation, the first effective equation, is not a big surprise. Yeah? Indeed, the first Maxwell's equation we are starting with is a nicely linear equation. You can directly pass the weak limit, no problem. So the problem lies in the second equation, where we have this product of epsilon eta, highly oscillatory, high contrast, and E eta, which is also a highly oscillatory field. And so we cannot pass to the limit in the product. Okay. The second thing you should note is that this system is unfortunately not in the standard Maxwell form. Yeah, because we don't have the curl of the magnetic field equals something, but we have the curl of hat m times h equals something. Okay, but this can easily be solved, namely by using a trick which is very popular among mathematicians, namely by defining a new object. And we just define hat h, a new field, but hat m times h. And we also write hat e instead of e for consistency. And with these new fields, we indeed obtain a standard Maxwell system, because the second equation now reads curl hat h equals minus I omega hat n hat e, and the first equation becomes curl hat e equals I omega, and now hat m to the minus 1 times hat h. Yeah? So with these new fields, we obtained an effective Maxwell system with new effective parameters. In particular, the effective permeability is given by this matrix hat m to the minus 1. Okay, and it's a matrix, by the way, because we have anisotropic effects here. Yeah, so it's really, it depends on the direction. Okay, and before discussing these new parameters, mu and epsilon, let me just say that, of course, these new fields are not just auxiliary constructions. In fact, they have a very clear meaning, and we will come back to this a little bit later. Okay. So, the sign of the effective permeability is determined by this matrix set M, and therefore governed, now let's have a look here, by this parameter lambda k. So, the other ingredients are more or less constants, let's say. They don't matter so much. The lambda k is the important part here. And what one can do now is one can now balance the two geometric parameters, alpha and beta, in the blue terms. Yeah, so alpha was a parameter in the thickness of the slit, and beta in the thickness of the ring. So one can balance these parameters in such a way that the real part of lambda k becomes very large in absolute value, and even more important, of desired sign. So you can really decide which sign you need. And this in turn can effect that the effective permeability can indeed be negative for a certain range of frequencies and in certain directions. This is possible. Okay. Now, okay, so in the following, of course, I would like to give you some idea of the proof. And actually, the method of choice is this so-called two-scale convergence. So many of you will know two-scale convergence, invented by Grégoire Lair in 1992, is a special type of weak convergence, which is tailor-made for periodic homogenization problems, and which, by contrast to the standard weak-L2 convergence, carries also information about the microscopic oscillatory behavior of the sequence in question. So in particular, our electric field and magnetic fields, they have two-scale limits, E0, H0, which depend on a macroscopic variable x, and this is the special feature, also on the microscopic variable y, which denotes somehow the position within a single periodicity cell. So in particular, the dependence of E0 and H0 on y characterizes the local oscillatory behavior of our fields. And so, as a consequence, or one of the consequences, the classical weak-L2 limit is related to this two-scale limit by simply averaging over this local variable y, by averaging out the micro-oscillations. Okay, and in view of this, the key point of our proof will be an exact understanding of this local y-dependence. And this is usually done by deriving PDEs that govern this y-dependence, namely the so-called cell problems. Okay, so let's start with the electric field. And actually, it turns out that the derivation of the cell problems for E0 is quite easy, providing relations for the curl, so it's microscopically curl-free in the periodicity cell y. It's divergence-free outside the ring, so this is a strange symbol. We'll come back to this, but this is the symbol for the ring in the cell problem. And the electric field vanishes in the ring. Okay, now I mentioned that it's not very hard to derive these relations, and just to get used to this, let me maybe explain how this works roughly. So actually, the curl-free condition is a direct consequence of this first Maxwell's equation here. Why? Well, in order to derive the microscopic curl of E0, we have to multiply the equation by eta, because remember that, okay, so that h eta is approximately like the 2-scale limit h0 evaluated in x and x over eta. And so if you want to get the microscopic curl with respect to the y variable, you have to compensate for this 1 over eta. So you have to multiply by eta and then pass to the limit. So the left-hand side gives the microscopic curl, while for the right-hand side, we exploit that with the eta in front times something bounded in L2 converges to 0, so it vanishes. Okay, the second divergence-free condition is even simpler, because note that epsilon eta is simply equal to 1 outside the ring. Yeah, this is how we defined it. And so taking just the divergence outside the ring, we get the divergence of E0, the microscopic divergence, basically, up to constants and up to eta. And on the left-hand side, we get the divergence of a curl which vanishes. And this last condition, well, this is a little bit more tricky, more technical, but it's basically because you can prove that this right-hand side here is bounded in an appropriate sense. And then since epsilon eta is very, very large in the ring, the electric field has to be very small in order to stay bounded, and then it vanishes in the limit. Yeah, this is basically how it works. Okay. Anyway, so at the end, it's also not very difficult to solve these cell problems. And so we find 3 basis solutions which are normalized by average, yeah, so corresponding to the 3 components of the electric field. And so as a consequence, the 2-scale limit E0 can be written as a linear combination of these 3 basis solutions. And due to the normalization by average, also the prefactors are well known. They are simply the 3 components of the classical Wigel-2 limit. Okay, so one easily obtains the full information on the electric field. By contrast, the analysis of the magnetic field is much more complicated. So first of all, we are still not able to pass to the limit in this product. So for the electric field, we could overcome this somehow, but for the magnetic field, we can't. And for this reason, we simply introduce a new auxiliary field, the so-called current J eta, which is basically this right-hand side here, up to constants, it's up to eta. For this current, we can also prove that it has a 2-scale limit called J0, for which one can show that it's divergence-free. I mean, of course, it's basically the curl of the magnetic field, so it's divergence-free. And we can prove that it vanishes outside the ring. So it's concentrated in the ring only. And now I would like to mention a very important fact, which you might have noticed already before, but here it becomes really important. So remember the scaling of our microstructure. So the rings were chosen to be very flat, and the slits were even thinner, which means that in the limit, as eta goes to 0, the ring becomes flat, really 2-dimensional, and the slit closes. This is even more important. Yeah? So the ring in the cell problem is a closed 2-dimensional ring. We have a change of topology in the limit. Okay, this will be important. And at the end, one obtains a coupled cell problem for this pair of H0 and J0, which I don't want to show you here. It's really complicated. But instead, let me tell you that exactly as for the electric field, one finds 3 basis solutions to the cell problem, which are normalized by average. However, this is not the end of the story. Yeah? So there exists a 4th non-trivial magnetic field with vanishing average. And since it's so important, I would like to give you a rough idea of this field, because it's not really difficult. So for the moment, assume, just for simplicity, that our ring in the cell problem is one-dimensional instead of two-dimensional. Okay, and now this J, this current J or J0, we set it that it's divergence-free and that it vanishes outside the ring. Divergence-free means that the normal component has no jump. Since it vanishes outside, this means that J0 has to circulate in the ring. In turn, the corresponding magnetic field is pointing through the ring, through the closed ring. And this is exactly the core idea of our fourth special solution. Yeah, so it's a magnetic field pointing through the ring. And yeah, we could make this rigorous in our central lemma, which states that the solution space for the cell problem for H0, J0 is in fact four-dimensional. Okay, so we are almost done. Let's go through the steps once again. So in the first step, we derived the full information on the electric field, which was easy. For the magnetic field, we had to introduce this current J eta, and we derived a coupled cell problem for the pair H0, J0. Okay, we then found out that the solution space to this problem is four-dimensional, and so in particular the magnetic field H0 can be written as a linear combination of our four basis solutions, in particular including the special magnetic field pointing to the ring. Now, why aren't we done yet? So why don't we still don't know everything about H0? What is missing? So the problem is that at this point of the proof, we don't know the amount of the special magnetic field pointing through the ring. Because it's mean-free. We cannot recover it from the components of the classical Wigel-2 limit. And this is a really delicate point, so this is quite technical. What one has to do, we called it the slit analysis, is getting back to the level of eta positive, so previous to the limiting process, and then very, very carefully analyzing electric field in the slit and in the rings by choosing appropriate test functions and using Stokes' formula, which relates the magnetic field to the electric field and so on. So this is really delicate, but at the end, one obtains a linear relation between H0 and the other components. In particular, the parameters lambda k appearing in this relation are exactly the lambda k from the main theorem, where, if you remember this balancing of the blue terms, they were really responsible for the sign of the effective permeability. So it's really a resonance effect here. Yeah, this special magnetic field has to be large in order to change the sign. This is how it works here. Okay, and once this is done, the very last step is a classical step when one has to derive the final macroscopic equations, but this is easy again. And we will come back to this step when talking about wires, because in the case of wires, it's exactly this last step which is the important one. Okay, so to conclude the first part of the talk, let me sum up. So we considered here a scattering problem for the time harmonic Maxwell system, where the scatterer has a fine microstructure consisting of many small flat split rings, highly conductive. As a main result, we obtained a homogenization limit and found that for this special fields hat H and hat E, we have an effective Maxwell system with an effective permeability in particular, which indeed can be negative, which is based on the resonance effect and the magnitude of our special field. And this is despite the fact that we started with a permeability which was constantly equal to 1 everywhere. And this is the reference to the paper by Guy Bouchetté and Ben Schweitzer, which was the original paper which treated this the split ring structure in the circular case. Okay. Now, in the remaining time, I would like to explain what happens if one adds wires to the split ring structure. And as already mentioned, we assume that a single cell contains one split ring and is 3 wires connecting opposite faces of the cell. Yeah, so in particular, the wires are running through the cells without gaps. And let me emphasize that it's really this connectedness which at the end leads to contributions in the effective system. If the wires were not connected, they had no effect at all. So again, the topology is really important here. This is the central contribution. Okay, now once again, since in practice the wires are very thin, as you have seen, we impose that a single wire has radius of order eta squared, meaning relative radius of order eta, so very, very thin again. And in order to model the high permittivity in the wires, we simply take epsilon eta from the first part of the talk, and we supplement it with an additional case, namely the case of wires. And there we set epsilon eta to epsilon w, some complex constant, over eta squared. Yeah, so again, very high conductivity, permittivity in the wires. Now, of course, this parameter epsilon w, this material parameter, characterizes the permittivity of the metal that wires are made from. And we have to assume already here that the real part of epsilon w is negative. So we are starting with a negative permittivity. But if you remember the beginning of the talk, a negative permittivity is quite common for metals. So this is perfectly satisfied in practice. We can assume this. Okay, and again the question is what happens in the limit as eta goes to 0 in this new situation? And the answer is very similar to those from the first part. So again, for the special fields head H and head E, which did not change, they are exactly the same as before, we obtain an effective Maxwell system with new effective parameters mu and epsilon. In particular, it turns out that the effective permeability is exactly the same as before. Nothing changes. The wires do not contribute. The effective permittivity, however, is given by the old permittivity coming from the rings alone, plus pi gamma squared epsilon w. So in particular, with a negative real part of epsilon w, which we actually assumed, one can achieve that the overall permittivity can indeed be negative.
Gamma is what?
Sorry?
Gamma is what?
Gamma was in the radius of the was a parameter in the radius of the wires. So it's just a fixed parameter here. Okay, and I mean this is exactly what is meant by the coupling of effects. Yeah, so the wires can change the permittivity without affecting the permeability. So without destroying this very fine resonance effect created by the rings. This is important. And I mean the effect of the wires is also global in omega, so it does not depend on the frequency. So it cannot happen that you have a range of omegas for which the rings work and another range for the wires where the wires work and they don't intersect. This does not happen here. Okay. Now before proceeding with this proof, let me say a few words on this on the special fields head H and head E, as I already mentioned that they have a very special meaning. And to understand this, you have to remember once again that the 2-scale limit is related to the classical weak L2 limit by simply averaging over this local variable y. So by taking the volumetric average of the 2-scale limit with respect to y. Now, of course, the volumetric average is not the only way of averaging. There exists also something called the geometric average. And for the geometric average, one takes the 2-scale limit and integrates it over integrals over lines, which connect opposite faces of the cell, exactly as the wires do, and which stay away from the ring. Yeah? And it turns out that head H and also head E, which by some, let's say, kind of coincidence is exactly the same as the classical weak L2 limit, they are both such geometric averages. So in other words, the head H and head E can be understood somehow as the weak limits of H eta and eta outside the rings, in some sense. And for our Maxwell system, this is exactly the right notion of effective fields. So these are really the relevant fields. And I mean, you could ask yourself, of course, why is it for the electric field that it's exactly the same as the volumetric average? The reason is simply that the electric field is curl-free. Yeah? So all line integrants are the same, which means that the volumetric average coincides with the geometric one. This is not the case for the magnetic field. This is really something different here. Okay. Now let's see how the proof works. And actually we have to proceed analogous to the first part, starting with the derivation of the cell problems. And it turns out that this is a very, very easy task because nothing changes. So the wires do not contribute at all. Why? Well, the reason is simply the scaling of our microstructure once again. Yeah, so remember that the relative radius of the wires was chosen to be of order eta, which means they are very thin. And so in the limit as eta goes to 0, these wires shrink to one-dimensional lines. And these one-dimensional lines are not visible in the PDEs. Yeah, so for instance, this divergence-free condition, which is a priori only valid outside the rings and the wires, so this is the symbol for the wires, is equivalent to saying that the divergence vanishes outside the ring only. Yeah, the wires have a so-called vanishing H1 capacity, so they are not visible in the PDEs. In particular, we obtain exactly the same characterization of E0 as a linear combination of our free basis solutions, which are exactly the same as before. Okay, concerning the magnetic field, the situation is similar. So also there, the wires do not contribute, they are not visible. And we find our old characterization as a linear combination of our 4 basis solutions with exactly the same prefactors. Okay, so the wires seem not to contribute at all. Okay, this is true, at least at the level of 2-scale limits. But they do contribute, this is the important point, when passing to the macroscopic equations. This is the last point I would like to explain. Okay, so what one usually does once one has the full information on the 2-scale limits, which we have at this point, is one multiplies the equation in question, so the second one is the important for us, with a so-called oscillatory test function, which depends on the macroscopic variable x and this microscopic variable y. And then one evaluates y in x over eta and passes to the limit. Now the problem in our case is still this product of epsilon, eta and eta. We cannot pass to the limit. However, it is quite easy to overcome this problem at this point of the proof. Namely, the idea is to restrict ourselves to only those microscopic test functions which vanish in the inclusions. Why does this solve the problem? Well, outside the inclusions, epsilon eta is simply equal to 1. So if you take a test function which lives only outside the inclusions, the problem with the product does not appear anymore. And moreover, since we also want to integrate by parts on the left-hand side of the equation, we also demand that our test function is microscopically curl-free, because otherwise, if it was not curl-free, this x over eta dependence would pull out a 1 over eta, which blows up. Okay. Now, one could, of course, ask oneself, why are we allowed to restrict the test function, the class of test function? So, because usually, in order to derive certain relations, you need to consider an arbitrary test function. The reason is that at this point, we already have the full microscopic information on our fields. So we already know how H0 and E0 behave microscopically. Yeah? So at this point, in order to derive the macroscopic equations, we are really allowed to switch off the effect of epsilon eta. Yeah? So it's not that we just ignore this product, because we already used it before, for instance, in the slit analysis. So there we really analyzed this product of epsilon eta and eta in order to derive the 2-scale limit. And I mean, of course, you could say, well, okay, this is true for the rings, but for the wires, we did not use the microstructure so far. So how does this work? This is true, and this is exactly the reason why such a test function does not exist. I mean, except for the trivial one. And we don't want to use it, of course. Okay, but let's do this step by step. So let's first of all ask the question. We know that it does not exist, but let's ask the question: can we construct such a test function? And actually, there's a very natural candidate for that, namely the electric field. Yeah, so remember, the electric field was indeed curl-free, and it vanishes in at least one of the inclusions, namely in the ring. It does not vanish in the wires, this is a problem, but it vanishes at least in the ring. Okay, there's a small technicality because for our test function we demand that it vanishes in the inclusion with thickness eta, while here the ring is very flat, but this is just a technicality. The more important point is that it does not vanish in the wires. But okay, anyway, so the three basis solutions to the cell problem seem to be a good starting point. Okay, and in the following we will just stick to k equal to 3, but so we will consider direction E3, but keep in mind that it has to be done in all directions. Okay, so the idea is to construct a test function with mean value E3, which is curl-free, which vanishes in all of the inclusions. And the question is, does such a test function exist? And yeah, so let's see. So actually the curl-free condition, first of all, tells us that this test function can be written as a gradient of some periodic potential, psi3, plus the mean value E3. Now, in order to have zero values in the inclusions, there is no other choice. We have to fix the value of this potential to minus y times E3 in the inclusions, yeah, in the ring and in the wires. And actually, this is possible in the ring and in two of the wires. But it's not possible, and this is the main point, in this third vertical wire here. Why? Because E3 times y is simply equal to 1/2 of the lower upper phase, and it's minus 1/2 of the lower phase. And so this contradicts periodicity. It's not possible. Now at first sight, this of course seems bad news because this makes the calculation more complicated. But at second sight, it is exactly this contribution from the wires which leads to really an effect in the effective system. So this is really the important point. And note that if the wires were not connected, so if they would not connect the upper and the lower phase, there would be no problem in constructing the test function which vanishes in all of the inclusions. So it's really the topology disconnectedness which causes trouble, and at the end leads to the main contribution in the system. Okay, so the best thing we can do is construct a test function which is curl-free and which vanishes in the ring and two of the wires, but which has a certain fixed value, and in our case this will be E3 in the third vertical wire. And so at the very end we will be working with a sequence of test functions with the property that they are curl-free, they vanish in the ring and two of the wires, but they have the fixed value E3 in the third vertical wire. And they are close to the electric field, in fact, so the electric field was a good guess, in the sense that they converge strongly to E3 in L2. Okay, and with this sequence of test functions at hand, we can now pass to the macroscopic equations. So, therefore, we multiply our equation with an oscillatory test function which uses the sequence theta eta 3 evaluated in x over eta times some macroscopic test function phi, arbitrary test function. Okay, and so we test our equation. On the left hand side, we first integrate by parts, exploit that our test function is microscopically curl-free, which means that the derivative only hits the macroscopic test function. We then use that h eta converges in two scales to h0. Theta eta 3 converges strongly to E3, so weak times strong convergence is fine. And so we end up with a double integral over x and y. And now, by simply evaluating the y integral, we end up with an x integral over head h, the geometric average, times E3 wedge gradient of phi. And of course, it is not really obvious at this point that this average gives us head h. So you have to believe me here, there is some calculation in between. But it's at the end, it's really the geometric average. Okay, and then we're writing this as a curl and integrating by parts once again, we find an integral over curl head h times E3 times phi. Okay, on the right-hand side, we proceed in an analogous way. So we first skip this third wire integral. We have to exclude it, but then we use that outside the ring and the two wires, epsilon eta is simply equal to 1, which means that we can use that E eta converges in Two's case to E0, theta eta 3 converges to E3. We can pass to the limit, obtaining a double integral over x and y. And now, once again, by evaluating the y integral, we find minus I omega epsilon effective r, so some effective parameter, times het E times E3 times phi. Okay, and since the macroscopic test function was arbitrary, we end up with the relation curl het h times E3 equals minus I omega epsilon effective r het E times E3. However, this relation is only valid up to this third wire integral, which we had to exclude. And at the end, it's exactly this wire integral which plays the central role. Okay, so let's see. Here on the left-hand side, we have our missing wire integral. We plug in the definition of epsilon eta, which was epsilon w over eta squared. Yeah, so in fact, we want to pass the limit in this right-hand side here. And the result of this limit process is, you can see it here, it's in fact not very surprising, but it's surprisingly hard to show. So the result, so the proof is quite technical, and I won't present it here. Instead, I would simply like to convince you that this result is exactly what one would expect. And so this is the very last thing. So therefore, remember the scaling of our microstructure. So we have chosen the wires with a relative radius of order eta, which means that the relative volume fraction of the wire is of order eta squared, so radius squared, times length of order 1. So it's of order eta squared. And so by dividing by eta squared, we are doing nothing else but taking the average up to constants, the wire averages. And in view of this, it is not very surprising that these wire averages converge to a double integral over x and y, and the y integral is simply a line integral over the third vertical wire over E0 times E3 times phi. And now the statement is that this is exactly the geometric average, but this is how we defined the geometric average. So it was exactly defined as a line integral of the two-scale limit over lines that connect opposite faces of the cell, like the wire, and which stay away from the ring. And this is exactly what is stated here. Okay, and this is basically the proof. And so at the end, we obtain the main statement, namely the contribution of the wires gives a new factor of the form pi gamma squared epsilon w, which can make the overall permittivity indeed negative at the end. Okay, and so with this I would like to close and sum up again what we've seen here. So we considered here a scattering problem for the time harmonic Maxwell system. Yeah? We assumed that the scatterer has a fine microstructure consisting of many small, flat, periodically distributed split rings and wires, both highly conductive. As a main result, we obtained that in the homogenization limit, the geometric averages het h and het e satisfy an effective Maxwell system with new effective parameters mu and epsilon, given in terms of the microstructure of the parameters of the microstructure. And actually, we found that with the right choice of the microstructure, both the real parts of the effective permeability and of the effective permittivity can both be negative at the same time. The effect of the rings is in fact a resonance effect based on the special magnetic field pointing through the ring, while the effect of the wires is just an averaging effect. It's nothing else. It's just averaging. But it's not just averaging, also the topology, disconnectedness of the wires, plays a central role. And then both effects together lead to a negative index of refraction. Okay, and with this I would like to thank you for your attention.
Very much. There's some questions.
many questions, but okay. Please
Okay.
go ahead. Go ahead. Okay.
Well,
Any question? But maybe
just one, and then.
Yeah, just one. Is it really important that the wires are straight, or they could be bended?
They could be bended, in fact. So there would be a slightly different contribution, but they could be bended too. So it's important that they vanish, that they are not visible.
Sure.
Yeah, but.
Yeah, in the experiment of Shelby and Smith, I believe that was in the microwave.
Exactly,
regime.
yeah.
And I believe in that regime, the conducting wires would have still a positive real part.
Yeah.
I mean, you get the negative real part in infrared and optical.
Okay.
And, I mean, can't guarantee it, but I'm pretty sure that's the case. And,
Okay, this I don't know exactly, to be honest. So, so if you take metallic wires, you can achieve negative real part, but maybe in those experiments they've taken a positive one. So it seems that this effect of negative index is quite robust somehow. So it's in the experiment it works in a very wide range, surprisingly, of materials. While in the mathematical analysis there is a very fine resonance effect. So
and you don't think you could get it with shorter wires which are not disconnected? I mean, there's models that go back a long
there are very different models. This is just one. So there are different types of negative refraction mechanisms. So it could be that this is not the right thing. So that even homogenization is not the right thing. Could be.
Yeah, and then the optical people, instead of using the split rings, have used C-shaped things, so they've even simplified it to parallel wires.
Yeah, exactly. So this is another point we tried a little bit. It's the mechanism seems to be quite different, so it's mathematically harder. It should be basically the same, but we don't get it. So.
At the beginning of your talk, you mentioned that materials with negative mu and epsilon real part don't exist in nature. Is that actually some sort of a theorem? I mean, since continuum media also arise through some homogenization on an atomistic level, is there some G-closure statement which states that the class of microstructures which you may obtain from atomistic material never leads to something? Or is it more, I mean, something which experimentalists say?
Yeah, it's more a physical view. So I'm not aware of any really rigorous statements in this direction. So it's really the physical intuition which tells you, okay, so it's usually very close to one. I can't say, can't tell.
I mean, this is a very maybe just technical thing, but so in your regime it looks like the importance. So there is an importance of the for the parameters you choose, such as the geometric quantities alpha, beta, and gamma.
Yeah.
But then I wonder. So, but then you choose a very specific scale in which you go. You take the thickness. And so what happens if you change rather than the parameters in front of the scalar, just the scale? So instead of eta to the fourth or other powers, I don't know. Do you know that there are some other extreme regimes that you
so in
cover
fact,
with other scales?
Okay, so in fact, both regimes, so for the rings and for the wires, are one parameter scaling. So you can change one scaling. So in the rings, for instance, the thickness of the rings, you can change it, and then the others are fixed in order to make our theorem work. So it's a whole, it's a one parameter family, and it's also the same for the wires. And as I said, it's a little bit strange because in practice, this is quite stable.
It's robust,
it's
very
somehow
much dependent on
this is why I don't know if really homogenization is the right thing to do. So it's one approach to get this effective behavior, but it might be not the right one. So maybe you don't have to take the limit as theta goes to 0. I don't know.
Another question?
Yeah, I will come back to your same question, but really precise. So the thickness of the split ring is exactly of the same order as the thickness of the wire. Is it important or not?
No, no. The wires have to vanish. It's an averaging effect. They can be even thinner.
But
the square root of
yes.
I mean, at least
No.
it looks like.
No, it's not important. No.
But then, the thickness of the split should be the square of the thickness.
It looks like, because it's alpha and beta, which very
right.
narrow, no?
Yeah. So the relation between thickness of the ring and thickness of the split of the slit, they are important, but not in relation to the wires. So they are independent.
And my point also is that there is no capacity effect. I thought in the first time that there would be some capacity effect for the wire, but no, not at all.
No.
No other questions left. Agnes, again.
Thank you.